Okay, but I think it's about time to start now. Okay, so I'm trying to keep an eye on whether other people want to come in still. But for the time being, let me just start. So hi, everybody. To start with, I wanted to say a few words about where we left off last time, just to get us in the mood again. So I'll try to use this pointer here to point out things. So, well, in some sense, the upshot of last time was the fact that we were able to look at the behavior and the Lorentz transformations of a massless vector representation. And so we basically built it up by building the field from these annihilation and creation operators, and we constructed some polarization objects, and we wrote the field operator as this mode integral. And then we just figured out from the basic group theory that we had developed that under a Lorentz transformation, A as an operator conjugated by the unitaries transforms as if it were a Lorentz vector with the index up plus a particular additional inhomogeneous bit, which was a specific function of the Lorentz transformation that we chose. So little lambda, capital lambda. And of course, we could calculate what that function was. So I'm just giving it here. But the important point was that unlike the massive vector representation, the massless vector representation does not transform as if it were a vector. And so if we were to write like our usual covariant theories where we contract vector indices, okay, up and down indices in the Einstein convention way, then we would not actually end up with a Lorentz invariant object. And so anyway, our conclusion was that A mu is not a good object to build the theory, but we can get out of it if we wanted to have a theory that allows us to be Lorentz invariant unitary local and causal at the same time. Then for a massless vector representation, we decided that we had to allow an arbitrary transformation parameterized by an arbitrary function lambda here and declare those two field operators to be equivalent. So A mu had to be equivalent in order to ensure Lorentz invariance to A mu plus d mu of some arbitrary lambda, and then whatever Lorentz transformation we choose, we could undo it by such a transformation. So whatever the parameter of the Lorentz transformation lambda, we can find a function lambda that undoes it. And so the way that this acts on the polarization vector was also just with a shift proportional to the momentum. And so the conclusion was, as it is in the box here, that Lorentz invariance, unitarity, locality, and we also put causality in there, imply that a massless spin 1 must have a gauge redundancy. And I said that we're going to do the same kind of manipulation for spin 2 now for the graviton. And so let me start with that, and that will be the last sort of purely group theoretic conclusion that we reach. And then we're going to go into soft theorems, which will allow us to further constrain beyond the group theory the low energy interactions. Okay, so now let's just go to massless spin 2. I will be more sparing on the algebra, which by the way, anyway, is more complicated in the spin 1, but just more complicated, not more conceptually difficult. So massless spin 2.
Julian, can I ask a question?
Yes.
So the point for the spin 1 is that we constructed the one particle states as being in a representation where the A's and B's act trivially. So if we hadn't done this, would it be possible to build a consistent theory of a spin 1 massless with no gauge invariance?
We had exactly the same question last time, and the answer is that no, it's not possible to make it fully consistent. So it's just if you want the, let's say, the polarization vectors and the rays on Hilbert space transform into different ways under Lorentz. How you can try and juggle around, right? So you change one way, but then the other way also changes in such a way that it's still not consistent. So there is no way of making those two consistent for the representations that we're interested in.
Okay.
Okay, so good. So okay, so massless spin-2, excellent. So now we have a representation which has momentum and plus minus 2 helicity. And we will represent this in terms of the field operator, which now has two indices, h mu nu of x, and equally the polarization vectors e mu nu plus minus, excuse me, now they're tensors, of course, of p. And actually one can use, well, if you go through the same algebra, one can solve the required constraints, one can use the following construction. So we have e mu nu plus minus of p, which is equal to e mu plus minus of p times e nu plus minus of p. So it's just the outer product of these e mu's and e nu's that we constructed last time for the photon. And well, there's, I guess, two comments. I mean, one is just those of you who have studied linearized GR, if we write these e plus minus mu nu, okay, if you use literally the expressions for e mu and e nu that we had last time, then those guys are actually the more familiar GR guys, e well, plus mu nu plus or minus I e cross mu nu. This notation is not great. I apologize. This allows me to point. Okay, very nice. So you see, this is like, you know, the plus and the cross polarization of the usual electromagnetic waves that you find. And these E plus minus refer to these plus or minuses. That's really unfortunate. Let me make this like a thick plus and a thick cross, okay? Just to emphasize that these are not the same. But what that means is that these E plus or minus mu nu that we are going to use, these ones here, okay, they are more like circularly polarized gravitational waves. But that's just a side remark. And the other side remark is that the fact that I can write the graviton polarization as an outer product of two photon polarizations is something that is also at the basis of this attempt to write gravity as the square of gauge theory, which is a recent interesting subject. I see that there's a hand raised. Pranjal.
Yeah. I had a question. So in this particular case, is there a physical, are the mixed polarizations physically important? Like if I have E plus mu and E minus mu?
I don't think so, and maybe this has to do with the fact that you have just two polarizations, and there come the correct two helicities, and the correct helicities are just the plus component and the minus component.
Mm-hmm. Okay.
Okay, but, so
yeah. Sorry, can I associate the scalar that I formed by as an independent scalar of the theory or something like? I mean, do you know of something like that?
No, I suppose this is the scalar degree of freedom that you project out if you go on the irreducible representation. You know, I mean, this is like the scalar degree of freedom is like the trace degree of freedom, and then there is, of course, a vector degree of freedom, which is a covariant derivative degree of freedom.
Right. Okay. Okay. Thanks.
Okay. So then the field operator. So h mu nu of x, so that's now given very similarly to what we had last time. So 1 upon 2 pi to the 3 halves sum over the plus or minus 2 helicities now times this integral. I think I called it d mu of p. And then, of course, we just have our EH mu nu of p, AH of p, e to the I p dot x, and then we have our Hermitian conjugate. Okay. And so then one finds, so the action of the little group onto E mu nu. So what do we find? Well, we find that, well, we can write it as, so we have the rotation part, which now has a factor of minus plus 2I theta. So this is just the helicity here, the factor H, E plus minus mu nu. Okay. And this is equal to lambda inverse mu rho, and then of course, as you might expect, you have a second lambda inverse nu sigma onto the E plus minus rho sigma of lambda p. Sorry, I don't know why let's just say action of Lorentz transformation on E mu nu. Okay. So plus, and then what you have is again two terms. So you have alpha plus or minus I beta divided by root 2k p mu lambda inverse nu sigma. And then on the first index, E, sorry, this, yes, you actually put the one of the vector versions of this in here. Okay, this is the E sigma. So plus now the other configuration of the indices. So A plus or minus I beta over root 2k, and then you have the index p nu, and then you have lambda inverse mu sigma, E sigma plus or minus of lambda p. Okay, so this is just a bit of more complicated, but you see it's essentially the same thing, right? You have an inhomogeneous term, so you have one. Sorry, I should not scroll like this. I said that with. It's going to be easier to make it into a video if I don't scroll like this. Excuse me. So you have for each index, okay, you basically roughly have the same story that we had last time. So you have one factor of the homogeneous lambda with one index, and then you have one inhomogeneous factor, each resulting from one of these indices. So it's the same thing that we had last time, but you just add an index because it's a spin-2 object. And then, well, you can simplify this a little, so let me do that. The simplification is that we can write this as, so we have the same guy, e to the minus plus 2 sigma, okay? But we can write this as equal to, so we still have the homogeneous part. Oh, okay, I won't do too much copy paste in case some of you are actually trying to take notes. That would be unfair of me. So lambda inverse nu sigma E rho sigma plus or minus lambda p. And then what you write is you basically write the inhomogeneous terms as, okay, plus p mu v plus or minus nu plus p nu v plus or minus nu, where I'm defining this v say mu plus or minus. This is defined as this alpha plus or minus I beta over root 2k. And then you have the inverse Lorentz transformation. I put it in like this: mu rho E rho plus or minus of lambda p. Okay, and so of course now this form here, okay, this p mu v nu, p nu v mu, that already reminds us of, well, first of all, it's a shift that is proportional to the momentum as, proportional to the momentum as we had in the spin 1 case, okay? But then you have this other thing here. And so instead of having the derivative, so p mu, of course, in real space becomes a derivative, instead of acting on a scalar function, it will actually act on a vector of parameters, which is essentially this v here, okay? So this translates into action on the field operator. So we get the Lorentz transformation of the field operator, okay, which will look very familiar. So what we find is that we take, we look at u, h mu nu u inverse, which of course depends on lambda, just maybe like this, okay? And so this gives me the thing that we expect. So lambda inverse mu rho mu sigma, so 2 lambdas. Then h rho sigma. And then we can write this plus d mu, and now we need a vector parameter, which is xi nu, which depends on lambda, plus d nu xi mu, which depends on lambda. Okay, and of course these guys are functions. Okay, so I remind you again, this is very similar to what we had in the spin 1 case, okay, where we just had d mu of some scalar function. And so what we have here is we have d mu of a vector of parameters, xi. And of course, in order to maintain symmetry, we have to find the symmetric derivative, which we do automatically, but that was also necessary for grounds of symmetry of indices. Okay, so we find ourselves now precisely in the same situation as we did for the spin 1 degree of freedom, except with slight extra complication due to extra indices. Okay, so we have the situation that Adrian was sketching again at the beginning in his question, which is that there is an inconsistency between the way that the state transforms in Hilbert space homogeneously under Lorentz, and the way that the field operator transforms inhomogeneously. And my statement is that no matter how hard you work, by adjusting one or the other, you can't go to a situation where they're both consistent. And so the way that we solve it is we therefore impose, thus we impose that, well, the E mu nu plus or minus of P, okay, that they are equivalent to E mu nu plus or minus of P plus P mu V nu plus P nu V mu, where these are now arbitrary parameters, such as exactly like the scalar parameter C that I wrote in our lecture on spin 1, and that the field operator H mu nu of x transforms as H mu nu of x plus d mu xi nu of x plus d nu xi mu of x, where xi mu is a free vector of parameters, an arbitrary vector function that we can use here to do this transformation. And so, of course, we identify this as, so this is linearized diffeomorphism gauge invariance. Okay. So specifically, if you want, this is the Lie derivative of the metric around a flat space with parameter xi. But it's precisely the diffeomorphism gauge invariance that the metric satisfies, the metric fluctuation satisfies around flat space. So this is the case for massless spin-2. Okay, so to sum up, by basically repeating the same logic, the same analysis as we did in spin 1, we find that there is also a redundancy that must be imposed on a spin-2 degree of freedom. And that redundancy is, as I was saying many times here, this is precisely this, this kind of gauge invariance. And this gauge invariance in the geometric language that we can use with hindsight is precisely what we would call diffeomorphism invariance around flat space. Okay, so the requirements of unitarity, of Lorentz invariance, of causality and locality lead us to the necessity to introduce this a very constraining symmetry, if you want, or principle onto the spin-2 massless degree of freedom of the Poincaré group. So just to say this again, I did it last time. I cannot see if all of you are raising their hands or not. So if I don't actually ask you, please ask your question after a while. Just switch on your microphone and ask your question anyway, okay? So very good.
I actually had a question, Julian.
Yes, yes. I did not see your hand. Yeah, go ahead.
So it's about the polarization vector for spin-2.
Yeah.
So it's supposed to be an eigenvector of the J3 generator, right? But I don't see how this generator acts on the polarization vector, because the way we constructed it, it's a rank 2 tensor.
Sorry. Let me go back here. So I'm just looking at my notes. No, I think it just acts in the tensor product. I mean, what's the subtlety there? I think it just acts in the tensor product.
So it acts like conjugation on the
just like the lambda. You know, once you have two indices, it's just acting with lambda on each index. It just acts on the.
Okay.
In fact, we have. I did solve that eigenvalue problem at CERN when we discussed the Weinberg-Witten, right? We
oh,
also,
yeah, that's true. Yeah.
Yeah. Okay. Okay. So for the rest of you who weren't in this lecture at CERN, we will actually do precisely this comment that I made maybe next week, I think. Okay, so fine. Now, let's go on then. Let me just make a comment which will also be nice in the sense that it will remind us of something that's familiar yet again. So what we would like to do now is we would like to actually make some objects that are invariant under these redundancies that we introduced. So we're going to look for, if you want, gauge invariant objects. Not exhaustive, we will just construct the field strengths for each of these, but it's still nice to see it in this context. So field strength for spin 1 and 2. So we see that somehow the fundamental, maybe in inverted commas, okay, so the fundamental spin 1 and spin 2 objects, so A mu, I guess, and H mu nu are not gauge invariant. So the question is, what are the natural objects that are? Well, we know, of course, that we know from electromagnetism that F mu nu, the Faraday tensor, which is d mu a nu minus d mu a mu, is gauge invariant. is gauge invariant. And then lo and behold, what happens is that F mu nu under Lorentz transformation, lambda goes to U of lambda F mu nu U inverse of lambda. And that guy transforms simply as lambda mu rho, lambda nu sigma, F rho sigma. So it also is a good Lorentz tensor, in this case, a 2 tensor. Okay, so this is precisely the pattern that we anticipated, that gauge invariance and Lorentz covariance are linked in this way. But this is not a particularly surprising story for any of you. Let's just say that in exactly the same way, we can do this for gravity. Okay, again, I don't think for you it's going to be very surprising, but the object that we construct, okay, if you play around, the object that gets rid of the inhomogeneous bits is the 2r mu nu rho sigma, and this is going to be equal to 2 derivatives d nu d sigma of h mu rho plus d mu d rho h nu sigma minus d mu d sigma h nu rho minus d nu d rho h mu sigma. This is precisely analogous to the F, just adding one more index. And this guy, well, R mu nu rho sigma and lambda, and so this goes to U R mu nu rho sigma U inverse. That's of course just lambda, 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 lambda R. Allow me to write it like this. 4. So these are, so this is gauge invariant. And Lorentz covariant. Okay, and of course this is also the case here. This gauge invariant and Lorentz covariant. That was somehow the point, that these two things are one and the same in our treatment. Okay, one requires the other. And well, let's box these guys because they're important. Oops, what was that? Okay, and then okay, excellent. So this is, of course, the linear. So we've discovered, if you want, the linearized Riemann tensor. Okay. So let me just pause for a second. Oh no, let me not pause for a second. Let me summarize this one more time in a hopefully clear way. So the conclusion is that theories of m is equal to 0 spin 1, okay, will then be constructed from gauge invariant objects that give us a U1 gauge theory. Okay. And we find that the m is equal to 0 spin 2, okay, they will be constructed from diffu invariant diff invariant, well, let me just be loose with the word, let me just call it gauge theory, okay. But the way that this actually plays out is that, of course, you write down now all the possible objects. Pranjal, I see it. Let me just finish writing this. You write down all the gauge invariant objects that you can. So, for example, f squared and contractions of the Riemann tensor and so on and so forth that don't leave any indices, so they're Lorentz invariant. okay, and you organize them, let's say, in a derivative expansion, and you find that this tells you something, that there is basically Maxwell and linearized Einstein, which appear as a consequence of these symmetries at low energy. So we've in some sense discovered, okay, these theories at low energy. So there's a great deal of universality of the behavior of photons and gravitons at low energy, simply because of these constraints that we derived over the last 2 lectures. There's at least one question of Pranjal's. Please go ahead.
Okay, I have a couple of questions here.
I said at least one because I thought there might be more people, but yes, could also be at least one coming from you.
Okay, so is there a conceptual reason why we could derive linear, a full gauge transformation of the U1 theory or U1 gauge theory, but only the linearized transformations of the spin-2 theory? Yeah, so that is the question one. I'll ask the second one up if this should I go ahead?
Oh, sorry. Is there a conceptual reason why? I don't know. I mean, maybe the reason is sort of trivial in the sense that linear is, you can only ever get linear, but linear is all there is to say for Maxwell, but there is more to say for Einstein.
Okay. Can I ask the second question?
Yes, okay. Of course.
In this case, I don't see how you could comment on what gauge group is arising from the transformations. How did you get the U1 and the diff group here from the transformations?
I was just maybe a little bit too fast here. So I did not mean to make that statement. I don't know how to write it then. No, they just have to be compatible with the transformations that we wrote before, and I agree that you can't make any inference on the actual group.
Okay, thank you.
I don't want to rewrite now what I wrote here on the slide because I don't actually quite know how to best express this using. Yeah. Anyway, yes, but the comment is important. So everybody, yes, I just wrote that because I was a little bit quick here, but the thing that I mean is that we only derived, obviously, the form of the transformation that we derived previously, which doesn't allow you to say anything about the group. Okay, so now there's another question by Manus, I think.
Well, I had the same question about how theory, the nonlinear theory.
You actually broke up. I think you were asking about how do you construct from this the nonlinear theory.
Yes.
So we will talk about how to go about this, not next time, but maybe the week after.
Okay. And my second question is whether you kind of built in the equivalence principle, or whether you
no, we'll actually, good question. We actually, if we have the time, we will derive the equivalence principle this week, but we will derive it actually by looking at some further input from low energy theorems, which actually are the topic of what I'm going to start now.
Okay, thanks.
Okay, any other questions? Doesn't look like it. So let's go right to work with this issue that Manus already started hinting at. So now this is all that I wanted to say about. So I see there are some more. Okay. Yes. Let me just finish that sentence. This is all I want to say in terms of remarks on group theory. And we will now go on, and we will work toward further constraining principles, which will come from low energy theorems, which is something different, as I will explain presently. Davide.
Yeah, sorry, Julian, I wanted to ask you, the field is not only, I mean, you said that it's not only a U1 field because we use the vector without the index and so on.
But I shouldn't have said that. I should have said it just is identified under this gauge redundancy that a mu goes to a mu plus d mu lambda.
Yeah, I wanted to ask you, in this perspective, a non-abelian gauge invariance instead, how would it appear?
Good question. You cannot derive, to the best of my knowledge, non-abelian gauge invariance that way.
So it's just like by hand modifying the gauge redundancies, thinking of an abelian.
It doesn't seem to be that the non-abelian gauge theories have the same origin in group theory as the abelian one.
Okay. Thank you.
My pleasure. Okay, so let's go on. So soft photons and gravitons. So this is a new chapter. So let's do that. Okay. Very good. So, so what we saw was that we basically made some technical advance by translating the statement of Poincaré invariance of the S matrix into certain kinds of gauge invariances for spin 1 and for spin 2. And that already gives us some very strong constraints. But we would now like to think about more constraints. Follow from thinking about IR physics directly, and of course of photons. So let me write photons often as gammas and gravitons just as g's. So let me start by just saying, what do I mean by a soft quantum? Okay. So what is a soft photon or graviton? Well, roughly speaking, of course, both of them, because they're null. Okay, their momentum is null, and what we want is roughly we want very low energy photons or gravitons. So if you have some sort of scattering or some part of a scattering amplitude in which you may have some massive particle or a charged particle that emits something like a photon at momentum q or a graviton at momentum q, okay, this will have some epsilon mu plus or minus, or an epsilon mu nu if you're the graviton. Actually, we can, oops. We can try and use some color. So if you're a graviton, then you're red and you have an extra index nu. So then we have here the momentum, outgoing momentum P mu minus Q mu. Okay, so then the point is that essentially we want to take Q mu to 0 with respect to any other energy scale in the problem. Okay, and well, Q mu, of course, sorry, I was touching the scroll button. Q mu, because it's null, it's actually equal to the length of the 3-vector Q mu. Okay, so if I take the energy to 0, then I also take the length of the 3-vector Q to 0. So the to put that in words, okay, it's a photon or a graviton that is emitted or absorbed as part of any process, okay, whose energy is much, much less than any other scale in the process. Okay, so that's why we send Q mu to 0. And so the reason why we want to focus on these, why do we want to focus on these? Well, that's because, as we shall see, these soft quanta, they basically give a natural definition. They give a natural definition of what we mean by charge in the case of photon interactions, and of mass or energy, if you want. Definition of charge and of mass in the case of a graviton. Okay, so I'd like to spend a little bit of time on the sense in which they give you a good definition of a charge and mass. And again, those who have been to some of these Solvay lectures I gave at CERN, they saw an abbreviated version of this in our discussion there. So what is the relation to charge and mass? Okay. So what we're going to do is we're going to consider a charged particle for now. And we're going to consider again some process. So you have here, let's say, the charge current J mu. We're going to write down actually a very concrete example of this. So I'm writing a general thing here, but I'm going to next go to a very concrete example, namely, just as an illustration, right? I'm going to go to to scalar QED. Okay, so we're going to see abstractly how I define this, and then we're going to see actually how it plays out in scalar QED, just to see that it's eminently sensible in the examples that we know. So you have some gamma emitted, and we have some momentum P, and we have momentum P minus Q. And of course, we will be interested in the limit that Q will go to 0 in the end. Okay, and we associate some amplitude M to this process, okay? But since it only involves one photon in the final state, okay, we know that we can write this as the contraction. It has to be some function M which carries an index mu, because this index has to be contracted into, well, because it's in the final state, into the polarization vector that we derived, E mu plus minus at momentum Q star, okay? So now let me just say there are two objects here, right? So there is the photon, and there is the particle itself that is charged, right? So this thing here is the current, okay? Something like, say, phi star d mu phi, roughly speaking, if phi is the particle that is charged, okay? So now we're going to say that we have a charged particle. So this corresponds to the charged particle of invariant mass p squared is equal to minus m squared. Okay, so this is not the photon. Of course, we know that the photon always has q squared is equal to 0, but there is now what we call the charged object. Okay, but because we take the soft limit, okay, in soft limit, we expand basically, if you want, in powers of q, and we only keep the lowest order term. So let's also assume, well, okay, we can say that here. We can also, just for simplicity, let us assume that this charged particle here has no spin. The same analysis is somewhat more complicated, but can be done also if the charged particle itself has a spin. But so in the soft limit, basically, what we find is that then this function m mu better only depend on this momentum, invariant momentum p. And it could depend also on spin labels, but it can't depend on q. But we have anyway said that there is no spin, so we're going to ignore these possible spin labels here. And so then, because these are the only things that we have available, we have that by Lorentz invariance, or more precisely covariance, the only thing that we can write is that m mu of p is proportional to p mu times some arbitrary function of the invariant mass. So it's just equal to p mu times f of minus m squared. Okay. So f is some function of p squared is equal to minus m squared. But actually, now just let me write the upshot before we take our break. Okay. This function is precisely what we would usually call is a constant that is associated with the particle charge. So this f of m squared is is what we call charge E, in the sense that in the soft limit, what we find is that m is equal to 2I times it. So this is just convention, the factors here, which we'll use, which we have to put in because we'll link it to this particular example later, times E times P mu E mu, let me put the plus and minus indices here, of Q star in soft limit. So soft limit, really, we expand in Q and we keep only the lowest order terms in all of these things. So precisely in the limit that Q goes to 0, right, this amplitude with the one photon emission is what gives us the definition of what we usually call E. And let me stop here. We could go on and argue for this more abstractly, but I think it will be most clear if we just calculate this very explicitly in some illustrative example, and you will see that it is exactly what you would usually call the charge. And so I think I want to start with that after the break. We'll take the break now. Of course, please feel free to ask some questions before. Questions, anybody? Okay, if not, then I'll see you at 1:15. All right? So use the other link, please.
Yeah.
All right, I'll end the meeting now. See you in the next one. Bye-bye.
See you.
Bye.
Okay, so I think I'll just carry on now. And oh no, there are more people trying to get in. Yeah. So, right, welcome back, everybody. I hope it's everybody. If not, I'll have to keep an eye on this wait room. So, good. So I've just recopied this last equation that we had, and I think it's really best to just go immediately through an illustrative example. Again, these illustrative examples, this illustrative example, but also the one we will do for gravity, they are just for visualization. Sorry, I'm admitting Michael. Okay, so these illustrative examples, they are just as a hindsight in some sense, because I'm going to just use Lagrangian theories that we know how to treat. But of course, the overall thrust, I keep repeating this, but the overall thrust of this part of the lectures is that we're actually developing those kinds of theories from, well, one might say more fundamental principles. Okay, but it's sometimes because we know Lagrangian theories and so on, it's useful for us to see that this actually makes sense in the context that we know and love. Okay, more people admit. All right, so illustrative example. So we'll take massive QED. So let's take the Lagrangian. So we have a charged scalar field which couples via the covariant derivative d mu phi. So let's give this guy a mass as we promised, phi dagger phi, and we have a kinetic term for our photon. So this is of course a very familiar theory, okay? And the way that we would have defined the charge here, or that we would have identified the charge coupling, is simply via the covariant derivative, which we write as d mu minus I e a mu. And we would like to basically isolate something like, you know, our friend here, this emission. So what we want is we want a coupling that is of the kind, you know, phi a. And so the culprit is the culprit is basically the relevant terms. So relevant terms. So this Lagrangian contains, of course, the minimal coupling i.e. a mu to the charge current, which I can write out a mu, and then we have our phi conjugate d mu phi minus d mu phi conjugate phi. Okay, the usual thing. Oh, let me get the cursor out of the way. Okay. Oh, sorry. There's someone else still waiting. So now get the cursor out of the way. Good. So as I said, the culprit comes precisely here from the minimal coupling terms. Okay. And so we read basically off the relevant Feynman rules, and we find that this kind of thing, M, in this case, precisely is given by I times, so let me write down the general diagram. Remember, we had P minus Q, and the photon carried away Q. So what we find is this guy, E, and then we get the derivative from the derivative in the charge current contracted into the polarization vector plus okay, P mu minus Q mu into E mu star of Q. And we are interested, obviously, as we said before, in the soft limit, in which case this becomes 2i, 2 pi to the 4 e p mu e mu star. Okay, I'm just writing the q, but it's of course you know, in the limit that q goes to 0 with respect to any other scale in the problem. And all I wanted to say is that really, if you naively take your favorite charge theory, such as this one with the such as this Lagrangian here with the minimal coupling to the photon, you write down using the Feynman rules what you get for a diagram like this. You find, well, you get something that's not exactly what we want, okay, but indeed in the soft limit, it precisely allows you to isolate what we would have called the charge, even in our naive way. And well, the normalization just is because I chose it to coincide, but of course, you know, up to some factors of 2 pi and I and so on, which we don't really care about. I mean, we fix those factors. What I'm trying to say is that you see that this defines charge, but in some sense, the factors in front of it are somewhat arbitrary. We don't care about them so much. But this is precisely the kind of sub-part of a physical process, the kind of sub-diagram that gives you a operational definition of charge. Good. That's really, that's all I want to say now. We will return to these kind of things anyway later on. and I guess we'll gain some more intuition about them. So there are questions. I don't know in which order they came. I think Pranjal first raised his hand.
Okay. So the question I have is whether this statement that we are making here is correct to all orders, all loop orders, or is it a tree-level statement that we just make that the charge is the coefficient will turn out to be the charge of the theory?
I think this is a question about renormalization, and I'm not entirely confident to. My guess is that not my guess. My answer would be that from the definition in terms of just the photon exchange, you can actually put the fully corrected propagator. If you stick in the propagator with the self-energy corrected there, then you get a renormalized charge that comes out, but it still comes out as a coefficient. Okay, so my guess would be that it's correct to all orders. Okay. No, my statement is it's correct to all orders, but of course we've only checked it to tree level in this particular theory.
Okay. Thank you.
Arunabha?
So I wanted to ask that, so this theory having a soft limit depends on the theory, right? Because for a Dirac coupled to electrodynamics, there won't be a P mu E mu coupling, right?
You can also do this for ordinary electrodynamics. It also has a soft limit, and I mean that's how you, for example, implicitly, if you calculate the Coulomb potential using just QED-Feynman rules, you're essentially looking at this kind of process twice in the soft limit. Is there something I'm missing about your question? I think it's fine. I mean, of course, I agree that the coupling will involve like gamma matrices and so on, but there's still a soft limit.
I'm saying that, I mean, the current will not involve derivatives on the fields.
Yeah.
So the coupling is through only gamma matrix and not through momentum. The coupling is not momentum dependent.
Yes, but that doesn't mean that you can't take the soft limit. So the statement is you can still take the soft limit and you will still find the charge vertex.
Okay.
Sorry.
Yes.
As for Arunabha's question, I think he's asking whether you'll have a gamma mu instead of P mu in the final expression, or whether in that case also you'll have a P mu multiplying the polarization vector.
I mean, the final answer can't have a gamma mu, and presumably you use some trace identities and it will get exchanged into a P mu.
Okay.
Arunabha, are you still have a question, or is the hand still raised because?
Oh, sorry.
Okay. Good. Manus. Manus, do you have a question?
Sorry, I didn't unmute. Is there an easier way to derive the charge than this? Or is there another way? That's maybe what I'm asking. Because this covariant derivative operator, for example, that also involves the charge. So isn't it just the coupling of some number to the field A mu?
Well, this is the Lagrangian perspective, which of course we used in order to show that in this case, our definition of charge coincides with the one that we had before. But what we're doing here is we're actually going to be relating the charge to certain S matrix elements. And so we never have to talk about a Lagrangian, right? So the first definition that I made is basically just relatable to an S matrix element.
No, yeah, I understand. But I was thinking, suppose you want to build a covariant derivative operator.
Yeah.
Using A mu, then you also need to introduce charge. But okay, you don't want to do that because you don't want to build a Lagrangian.
That's yeah. Okay, let me move on.
Thanks.
So now we're going to do the same thing for the mass vertex. So, well, let's write mass. but you've already basically seen all of the ideas. So now we basically have something like this, but now what it couples to is the energy momentum current, which we usually write T mu nu, okay? And the thing that we emit is one of these gravitons. But the idea is, of course, the same, that there's going to be this curly m, which now has to be m mu nu into the e plus or minus mu nu of q star in the soft limit, soft q. And so then what we write is, for precisely the same kind of reasoning that we used before, we write, so in the soft limit, we write that m mu nu is now 2 factors of p mu p nu, times some function g of p squared, which is, of course, the invariant mass m squared. P squared is equal to minus m squared. And we therefore have the curly m, which is equal to, with this convention, 2 pi to the 4th of g times p mu times the e plus minus mu nu star. Okay, and this is our definition of mass, or energy. I mean, the thing that couples to gravity, basically. So G is the gravitational coupling, if you want. G is gravitational coupling. Okay, so now, again, on the level of the matrix element, or the amplitude, this is the same. But now maybe the illustrative example that we get from hindsight is less obvious, but I think it will be very helpful, even more helpful, to go through this. So instead of doing scalar electrodynamics, what we're going to do now is we're going to do, we couple a massive object, a massive scalar, to gravity. So again, illustrative example. Scalar coupled to GR. Okay, I guess this is true for everything we do, but pay close attention, because what we're doing now, we're going to actually get back to later, in especially the case of gravity, because what we want to do as part of this course at some point soon, I hope, is basically to calculate the quantum effective potential between two massive objects. The thing that I briefly mentioned we would do in the very first lecture. And the calculation, well, we'll even be able to sketch out roughly what calculation to do now, but to go through it in detail, we'll have to, develop more of the apparatus first. But we're going to basically return to this theme now at some point in the not too distant future. So what do we have here? So we do this, we have the action S phi, so the scalar field now coupled to gravity, which is now 1 upon 16 pi g Newton. We have our gravitational action. Okay. But then we add the scalar field, and of course we couple this scalar field in the usual way, d4x minus g, and then what we have is we have minus 1/2 g mu nu d mu phi minus, well, we'll give it a mass m squared phi squared. And now, of course, we don't need a complex scalar because we're coupling to gravity, so we'll just take it real for simplicity. But again, the culprit is we want terms of the form phi phi h. Okay. But it is not so obvious where they come from in this theory. Well, it's kind of obvious, but you need to do a little bit of expansion. Okay, these come from, well, they come from expanding basically. So let us do this. So let's say that we look at S phi, which we keep the scalar, but what we do for the graviton is we expand it around Minkowski space. So we write at eta mu nu plus kappa h mu nu, where kappa is just, what is kappa? Kappa is 8 pi g Newton up to a fact, yes, up 8 pi g Newton square root. So it's just another way of parameterizing the Planck mass, Newton constant, whatever you want to call it. Okay. So, I guess as I mentioned once before, okay, I think I actually gave you this definition before, I remember now, but anyway, the point is that we have to scale h mu nu by kappa so as to get a canonically normalized kinetic term for h mu nu, which is of course our field of interest. Okay, so this guy here, that's equal to, well, it's just S phi eta mu nu plus d4x, well, there's this kappa here, and then what we have is we have the functional derivative ds phi d h mu nu at h is equal to 0, coupled to h mu nu at x plus higher order terms, but we wanted the phi phi h term, so this phi phi h term comes here from this. And of course, we can write this as S phi eta, okay, plus, and then you will all recognize by definition, and will not be surprised, that this is d phi, d4x kappa over 2 times h mu nu times t mu nu phi. So it's a bit difficult to write at the lower bottom here, around flat space plus dot dot dot, okay, where this object t mu nu is obviously the energy momentum tensor of the field phi evaluated around flat space. So let me write this. Okay, so flat space energy momentum tensor, which is T mu nu around flat space, which is equal to d nu phi minus 1/2 eta mu nu, and then the contracted indices d alpha phi minus the mass, excuse me, plus the mass contribution phi squared. Okay, so unsurprisingly, for those of you, which I guess includes everybody, who have studied gravity before, the coupling of matter to the graviton proceeds by the contraction of the graviton H object into the T mu nu. And the reason that such a coupling can be gauge invariant, even though H is not gauge invariant, is of course that T mu nu is covariantly conserved. So you can trade the derivatives, forget about the boundary terms, and the thing becomes gauge invariant again. But yes, Sergio.
Yes, the question is if we want a kinetic term for the graviton, we need h² terms, right?
Yeah.
And so couldn't that include other interaction vertices that we might consider?
And in fact, it does, and that will lead to the higher derivative type expansion in terms of an effective field theory of gravity, and we will classify all of these. But for the time being, we can just stay at with the treatment I'm giving you.
Okay.
But thank you, that was a good point. So M is then equal to I 2 pi 4 times kappa over 2 I p mu, okay, if I'm not mistaken, minus q nu, and then the whole thing plus where you swap the mu and the nu index. Okay, how many brackets? P mu into this. Okay, then mu changed with u, and then E plus or minus mu nu star. Okay, so in some sense, the straight generalization of what we saw for the scalar electrodynamics. And in the soft limit, we find that this goes to I times 2 pi to the power 4 p mu times, and then we're going to write this 2 times kappa over 2. Okay, because we had we had this factor 2 here, which we put by convention. I mean, we had put it out here, but that tells you that G in this case, so G, the gravitational coupling, is precisely is kappa over 2, which evaluates to 8 pi square root of G Newton, well, square root of 8 pi G Newton 2. As one would guess from, well, our knowledge of GR. Okay, so what's the point of this? It's just to illustrate that, again, to pick up also with Manos, if we were to work with the Lagrangian, which we are avoiding for the time being, I mean, we're just doing it as an illustrative example, then our previous definition of the coupling between the graviton and a massive object precisely reproduces the gravitational coupling that we would have naively associated from our previous knowledge of GR. And in fact, it's just essentially the square root of G Newton up to some factors. So what that means is that by looking at processes which involve these mass vertices and the charge vertices, we can hope to make some statements about how photons couple to charge and how gravitons couple to mass energy. And in order to maybe give you just a little preview, what's going to happen is that we will find that we find further constraints that the photon can actually only couple to charges that are conserved. So the sum of ingoing charges in any process has to be the sum of the outgoing charges. And the conclusion for the graviton will be much more striking, in my opinion. And the conclusion for the graviton will not be charge conservation, because there is really only one charge anyway, positive. The conclusion will be, in fact, that will be the equivalence principle, in the sense that if you couple the graviton to different massive fields, or say different massive objects, then the coupling strength will have to be the same for all of these couplings, or otherwise we get an inconsistent theory. And so this is like the S matrix way let's just say the exchange of quanta way of formulating the equivalence principle, which I think is quite a striking thing to derive from these principles. But we aren't there yet. I mean, we have to actually look at these soft theorems. So far I've only introduced the vertices, which will be of interest, but we still have some way to go before we can come to such conclusions. Now, let me spend a few minutes on a relation also of these two vertices to the potential, either between charged particles or between particles that are characterized by having a mass. So let's look at the two particle potential. Okay. And so just, I suppose, as a quick reminder, if you look at 2-2 scattering of, say, a charged field or a massive field, then you will probably remember from elementary treatments that essentially the first approximation, also known as the Born approximation, is nothing but the Fourier transformation of what we would call the potential with respect to the transferred momentum. Okay, this is nothing but the Born rule. The Born approximation. And so that also means that if you have the 2-2 scattering that is mediated by the exchange of either a photon or a graviton, then by doing the inverse Fourier transformation, you can actually deduce what the potential should be. And so let us do that now. First, just to remind you how it works, I'm going to do it for the charged particle. And then I'm going to give you a quick preview of what the result will be for the graviton. Okay. So the vertex diagrams basically that we have defined, they basically give us definitions of charge and mass in a mathematical sense, but they don't actually correspond to physical processes because they don't conserve overall momentum. They do, however, contribute to important physical processes as sub-diagrams. And so we can illustrate that by calculating the potential. So let's start with the charged scalar case. So what we have is we have, so you do something like 2-2 scattering. Okay, so we have the diagrams. We have the tree level diagram. So we have our two scalar electrons, scalectrons, and we exchange a photon between them. So we start with something like E1, E2. This one has momentum 1, momentum 1 primed, momentum 2, momentum 2 primed. And we're exchanging the momentum q mu here. And then we have plus, essentially the same guy, except now we can have a loop in the middle. The labels are the same, okay, and plus ... And what we have is we have the V classical, okay, plus we have a first quantum correction of the potential V h bar. Well, let's just say, so this is basically the effect of vacuum polarization. Well, as we see actually very explicitly here, it's the effect of including the process that you have a virtual particle-antiparticle creation and annihilation in the process of exchanging this photon. Okay, so what we can do is we can incorporate this. We can incorporate the vacuum polarization effect very simply by using instead the corrected propagator I for the photon. So IP mu nu is going to be mu nu standard one plus the one with the loop, mu nu plus higher orders. And as is done in any sort of beginner's quantum field theory course, this can be written as, this can be basically resummed as a geometric series where you have the free propagator, which would just be the eta mu nu over q squared, minus this self-energy contribution pi of q squared. This pi of q squared, okay, this is just some integral which can be calculated. Some integral which involves, you know, like a logarithm in particular, which depends on the mass of the particle and the momentum q squared, of course, in a dimensionless way. But what is more interesting for us is that I can just pick out the first two contributions here because these are the ones that I want to illustrate. So I have the eta mu nu, the usual one, and then I have precisely this term pi of q squared here, eta mu nu plus dot dot dot. Okay, and we really want to associate them. So we want to associate this one to this diagram and this one to that diagram, and so on and so forth. So then what happens is that we can very simply write, so we can extract the following contributions to the 2-to-2 scattering process. So we have up and this one, tree level, E1, E2. So what do we have? We have, this is E1, E2 divided by q squared times eta mu nu. Okay, so I just have the charge vertex if you want. I'm neglecting now the factors of 2 pi and i's and so on. Okay, but I have just these two vertices. I multiply essentially the eta mu nu over q squared part of this. Okay, because that contributes just to that part of the photon line. And then I have the diagram which has the vacuum loop in the middle. So I have this guy, loop, that guy, E1, E2. And what does that give? Well, it gives E1, E2 over q squared eta mu nu from what we had before. And then I have our friend pi. Okay. And so now what happens is that, well, the first bit is done in every single elementary treatment on quantum field theory. So in the non-relativistic limit, which is when you want to extract the Coulomb potential, the instantaneous Coulomb potential, you get basically, well, Q0 is much, much less than Q. Okay, this is the non-relativistic limit. Okay, so what you can do is you can basically you can replace the invariant square Q squared with just the contribution from the 3-vector part, because that gives a dominant contribution according to non-relativistic limit here. Okay. So then what happens is that now let's see what you get from the first diagram. Okay. So that's the thing that I said is in some sense elementary. So you can write E1, E2 divided by Q squared. That is by the Born approximation is d3x e to the minus I q dot x v0 of x. Okay, so that such that v0 is precisely E1, E2 divided by 4 pi r, the inverse Fourier transformation. And that's, of course, the Coulomb potential, nothing but the Coulomb potential. The more interesting bit, which I wanted to draw your attention to, so now the next bit is the one that's important, okay? We get a correction, of course, we get an H-bar correction from the vacuum polarization. And that is from this term, okay? So that V of X, the total V, is actually our V0, so E1, E2 divided by 4 pi R, plus E1 squared, E2 squared, divided by, well, 60 pi squared times m squared. And then there's like a delta function at the origin. Okay. And actually this guy is known as the Darwin term because some guy called Darwin first incorporated it. Okay. So couple of comments. So as we said, there is like the classical term, but then we're also able to calculate in a systematic expansion the first correction here. And this first correction is a pure quantum effect. And that quantum effect in this particular case is the Darwin term, which happens to be extremely short range. I mean, I've actually taken a sort of a low energy limit. It's really, it is really a Yukawa type term where the range of the force is the Compton wavelength of the charged scalar particle. Or in real life, it's just the Compton wavelength of the electron. But for most applications, you work in a limit where you can really replace this by a delta function. And the point is that this changes atomic structure. So this is actually observable. Okay, this is totally observable. So for example, it would change the 1s or the 2s energy of the hydrogen atom. Contributes to the Lamb shift actually. But the point is there is a well-defined correction to the potential which comes from the diagram where I'm exchanging the photon, but it's loop corrected. Okay. So the point that I want to make is, the important point is that there is a precise analogy for gravity. Okay, so there's this analogy for gravity, which is the following. Okay, now what we do is we have two objects where now we don't have the charge current, but we have, you know, our energy momentum current, and what we exchange is a graviton. So this will give me the tree level, the Newton potential, V Newton, but then, so now the coupling is mass M1, M2 plus the loop diagram, plus, in fact, in this case, we have to also include loops where the graviton itself runs in the loop, okay, plus other terms. And so this is delta V H bar gravitational, and the result is actually that the potential will be V, which is equal to minus G Newton M1, M2 over 4 pi R. So this is comment 1. This is the Newton potential plus, and then you have some coefficient that we will calculate. There is going to be lots of pi's and things, but then if I write all the interesting dimensional constants, then this is a term that goes like G Newton H bar C to the power 3 R squared times the G N M1 M2 over R plus dot dot dot. But let me actually just write 4 pi here, which would only redefine these factors there. And so this is, if you want, the delta V Newton, the H bar correction. Okay, and so there is a couple of things that I was doing here at the same time. One is the more elementary point that I started off with is that there are physical manifestation of these charge and mass vertex diagrams. And one nice way of seeing it is, for example, they allow you to extract from the idea of just particle scattering what is a potential and make contact with such elementary notions as, for example, the Newton potential, but then, or the Coulomb potential. But then you can do much more fun things. You have basically the theory on your hands. In the charge scalar case is just a quantum field theory, so you can calculate loop diagrams and you find quantum corrections to the classical. Adrian, I see that you're asking a question, but we're almost at the end, so let me finish and then maybe you can ask your question then. So tracking back, you can get some quantum correction, which corresponds to using the quantum corrected propagator in this case. And then the point is that in the gravity case also, you can calculate the classical potential, and then we will learn how to use the gravitational theory that we construct as an effective field theory to actually get a quantum correction, which is fully a prediction of what we're going to develop. So this correction here, this depends only on things that we have under our control. So there is actually a correction of a quantum correction. There's a prediction of a quantum correction to the Newton potential that we will be able to calculate. But this is a preview, okay? Before we get there, next time we're going to use the vertex diagrams again, and we're going to use them to derive low-energy theorems, which will give us these constraints and how actually can you couple a photon to matter and how can you couple a graviton to matter. And once we know that, then we have, you know, symmetry constraints, we have dynamical constraints. We're then going to build the kind of interactions that are allowed. And then using those kinds of interactions, we will learn how to calculate with them using loop corrections. And we will end up calculating this, for example, this contribution here. So this is now chartering basically the path for the next few weeks we're going to take through this course. Okay, so it's probably a good idea to stop here, and we already had at least one question from Adrian.
So I have two questions actually. The first one is a bit vague, so I'm a bit disoriented here. Can you remind what is the connection of this to the previous discussion about soft limits?
Yeah, no, sorry. So I will return to the link, because what I wanted to do is I wanted to illustrate some physical quantities that you can associate to these types of diagrams for the photon, okay, and to this kind of diagram for the graviton. But the actual calculation of the potential here, that has very little to do with the soft theorems. The point is that the next chapter is if you want soft theorems. So at the beginning of next lecture, we will full force return to the actual soft theorems. Okay,
thanks. And the second question, can you go back to when you introduce actually the soft limits?
Yes. Let me see how best to scroll. That was actually was it already, it was in the previous lecture?
It was at the end of the previous lecture, I think, yes.
Yeah.
So it's just a quick comment. So when you apply the Feynman rule to quantify this diagram,
yep.
I don't know, I don't see it in this slide, but there was a sum somewhere when you apply the Feynman. So I didn't understand it. Are you summing two different diagrams, or?
No, this is just, you mean why you put P and P minus Q?
Yeah, at some point there was a sum inside of the scattering amplitude.
No, I think I know what you, I think I know what you mean. This here, oops. What? Huh? Okay, maybe that's in the other. Anyway, I know what you mean. That there was like P mu plus P mu minus Q mu.
Yes.
Yeah.
Exactly.
that is literally just the Feynman rule associated to this diagram. Just go through the calculation.
Okay, I thought we were summing two different diagrams or something.
No. This is really just that one diagram.
Okay, thanks.
Yeah. Sergio.
Yes, I guess I'm just a little confused because we introduced the gravitational coupling and we called it the mass. And then we calculated it for a scalar field and it doesn't correspond to the mass of the scalar field. And then in the end, we still use this coupling as the mass in the Newton's equation. I don't know if there's a link between this gravitational coupling and the mass.
Okay, good. Let me see. Let me go back to lecture 2. So, yeah, I suppose the link is precisely this, right? So, what happened was, so focus your attention on this thing. Okay?
Yeah, okay.
So what came out was we had like the square root of g Newton, which was the coupling, that's our little g.
Yeah.
But then we have two factors of the momentum, which is going to be m1, m2.
Okay.
Okay. Other questions? Manos.
Yeah, is there an intuitive way to root of g?
Again, you cut out in the middle, but I think there was something like, is there an intuitive way to see that it is square root of g?
Yes.
I mean, sorry, where would the intuition come from? I mean, if I do it in a Lagrangian way, then it's obvious just by dimension counting. But from the way that I'm trying to advertise here in these lectures, I don't know if I have good intuition. No, I mean, you can count the dimensions again, I guess, because you have one extra factor of p there, right? So if you look at it, yeah, I think that's probably it, right? So good. So in the in the charge case where the coupling is dimensionless, right? You had one factor of p here times your coupling. And so, of course, because now you have two factors of p, because it's spin 2, you have to have two indices here. And the only Lorentz vectors that you have at your disposals are p's, and they carry dimension. You have to make up that dimension by the dimension of the coupling. And then, of course, whether you call it square root of g or kappa or whatever is, yeah. But that's why it has to be dimensionful, whereas the spin 1 case is dimensionless. Okay,
and it's also related to the, you can probably write it in terms of the Planck length or something like that.
Of course, yes, absolutely.
Or if you introduce h bar and c.
Yes, indeed. Nice. In fact, that's of course what you should do if you were, yeah, I mean, no, actually there's no preference, but feel free to do it. Yeah. Any other questions? Okay, it doesn't look like it. So, well, have a good week, everybody, and see you next week. And let's hope again that as soon as possible we see each other again in the classroom, though it probably will be a few weeks. Okay, see you guys.
Thank you. See you.
Goodbye.
Bye. Thanks.
Bye.
Thanks. Bye-bye.